We discussed Gauss's law in the last lecture. And let us do some examples now. Okay. Now here's our problem. We have a sphere, not empty, a full sphere, a ball made of copper. It's conducting. Conducting means iletken. Okay? All right? And you have placed charge on the sphere. So the total charge on the sphere is plus Q, whatever Q is. Okay? And we want to find the electric field at any position R anywhere in space. First, let us think, what does conducting mean? Now, when you first place the charge plus Q on this object, of course, maybe you touch on one side of the object and you put all of the charge here. What will happen? All the charge is positive. Okay? What do positive bits of charge do? What kinds of force do they apply on each other? They are all positive. Two positive charges. Do they attract or repel? They all repel each other. So you put all of these charges here on this side of the sphere, and they all repel each other. So they will try to go as far as possible. Okay? If some of them were inside the sphere, as they try to go far away from each other, they will get as far as possible, meaning they will all reach just the surface of the sphere. Okay? They will try to do that because they are being repelled by other charges. Right? But whether they can do this or not is another matter. If this sphere was made of glass, for example, jump, we say glass is not a conductor. It's an isolator, yalıtkan. What does it mean? Well, in glass, electric forces start to push the charges around, and as we saw last time, there are other charges with which they collide. So inside any material, there is some amount of friction. In glass, the friction is a lot, so the friction forces can dominate over electric. Oraya oturmuyorsunuz lütfen, en ön sıraya. Over electric forces, okay? That means in glass, if you put all of the charge here, they try to push each other apart and move away from each other, but when they encounter friction, because they hit other atoms and nuclei and whatever in the material, and because of the structure of glass, that friction force is too large, so all the charge can remain on one side. That is what may happen in an isolator, at least for a while. Of course, after a while, the electric forces will gradually push them apart and they will equalize. But it is possible in an isolating material for stuff to remain, for charges to remain concentrated to one side of the body. Now we go back to our example, which is conducting, like copper. In that case, the friction forces, what we call the resistance, is small, very small. And electric forces will always dominate, they will be more powerful. Okay? So in a conducting material, the tendency of the electric forces to push all the charges, they are all positive, to push them away from each other, will be effective because the resistance, the friction, is very low. So in a very short time, they will all get to the surface of the sphere. Is this clear? So that is the difference between isolator and conducting. It's a property of materials. Which is why, starting from ancient times, people discovered that it is possible to charge one side of a glass piece positive and the other side negative. If it was conducting, you know, this doesn't happen with copper or iron or other materials that are metals that are conducting, because in that case the friction is so low that as soon as you try to separate them, they will come back together. If they are opposite charges. If they are the same charge, they will all move out to the surface. Once they get to the surface, they will not stay on one side of the surface concentrated, because along the surface they also push against each other. So in a conducting body, as soon as you put net positive or negative charge on it, in a very, very short time that charge will move to the surface and it will distribute itself evenly all over the surface. The density of charge everywhere on the surface, the charge density, the amount of coulombs per meter square, everywhere on the surface will be the same. Okay? Now let us apply our Gauss's law. Let me write here in summary what I've just told you. Conducting, little friction, resistance, okay? Friction against charge motion, we call that resistance, direnç. Okay? Charge moves to surface and distributes uniformly all over surface. Now let me say that my sphere is a big ball with radius r. Okay? Now let me start to calculate, to figure out what the electric field is. Well, clearly, all of space has two different regions, different properties. Inside the ball, okay, and outside the ball. So let me take it piece by piece. Let me now consider some radius r, any position r, inside. So, first thing I'm doing, R is a point inside the sphere. Now, the charges have moved to the surface, but no matter what, even if a bit of charge remains inside, and I try to calculate the electric field, I know that this system is a sphere. It is spherically symmetric around the center. Okay? And I want to find the electric field at a position here at R. I don't know at the beginning. Some of you may remember, oh, the electric field is 0, it's a conductor. I don't know that yet. Okay? I can guess that because inside a conductor, if there is any electric field, then charges will move. There is little friction. They will respond to the electric field forces and move until there is no electric field left. Okay? So we can guess already that the electric field is 0. But for the moment, let us not assume anything about the electric field. Let us not do this reasoning that it is going to be 0 anyway. Okay? Because we want to apply Gauss's law and see how it works. Okay? So when you start applying Gauss's law, the first thing you ask is the following. If I want to calculate the electric field at this point, what other points in space will have the same electric field? This is a question about symmetry, about the symmetry of the problem. See, what parts of the space are like each other? Okay? Now, if I want to calculate the electric field at this point, and the charge distribution, the problem I have, is symmetric. Okay? What other points have the same strength of the electric field as this point? Here's my point. At radius little r, let's say 2 centimeters from the center. What other points in this problem are like this point? What are the points? Okay, it's a sphere, 3 dimensions. It's a spherical surface. So let me show the spherical surface. I have a sphere of radius little r, which contains my point. Okay? There is spherical symmetry. All points on this sphere should have the same electric field. Okay? And moreover, what should be the direction of this electric field? If there is an electric field, it's a vector, what should be its direction? There is no negative. In this problem, okay, in general, of course, it points away from positive charges. In this problem, there is some positive charge. But the question I'm asking is simpler than that. Okay? The problem is spherically symmetric, and you are at some point r from the origin. The electric field may be 0, maybe something, I don't know what. Okay? But in a spherically symmetric problem, in what direction should the electric field point? Okay, let me put it this way. If I have a spherical ball here and I'm looking at some point inside or outside, doesn't matter. Is there any reason for the electric field to point this way? Here's my sphere. In a spherically symmetric problem, is there anything special about this direction? No. So why should the electric field point that way and not this way? Perpendicular to what? Right. In a spherically symmetric problem, everything is symmetric about the center of the sphere. For a sphere, there is only one special point, which is its center. Right? Which is our origin. So there is only one direction that you can make at any point, and that is the direction relating your point to the center. Radially outward. For a sphere, the only direction that spherical symmetry can define, can select, is the radius. Okay? Now, I don't know whether it's going to be inward or outward. That's not important. I'm not even considering this problem. In any spherically symmetric problem, any electric field, negative or positive or whatever, if there is an electric field, should point only in the radius direction or minus radius direction, of course. That will come when you calculate the magnitude of the field. If it's negative, it means it's pointing inward. But the direction must be along the radius. In a sphere, radial directions that remember where the center is, those are the only directions that can appear. Is this clear? That's what spherical symmetry means. Okay? Lütfen ön sıraya. Size söylemeyi unuttum ama. Arkadaki 4 sırayı boş bırakıyoruz bundan sonra. Emrah Bey, siz de buyurun. Oradan da neyse artık oturun, tamam peki. Uğraşmayalım. Siz gelirken görmedim, unuttum söylemeyi. Okey. Okay. So now I'm ready to apply Gauss's law. To apply Gauss's law, remember, I need a closed surface, and I always choose that surface as a symmetric surface, as a surface on which the electric field is constant. So I figured out if I want to find the electric field at this point here, at this point, okay, let me see if this one works. Okay, at this point here, I choose a spherical surface, which is this surface. Why do I choose this? Because in a problem with spheres with spherical symmetry, all these points will have the same electric field. Furthermore, the direction of the electric field is going to be along the radius. So E of R will be some E times, whatever it is, positive or negative number. I don't know yet, I haven't calculated it, but it will be in the radius direction. Is this clear? To apply Gauss's law, I need a closed surface, and as we showed the last time, Gauss's law holds for any surface. So you decide what surface simply depending on the problem you have. If you have a spherically symmetric problem, you choose a sphere, spherical surface, right? En öne lütfen. Okay. Yeni gelenler, oraya oturmuyorsunuz. En ön sıraya lütfen. Okay, so here's our problem. Here's our surface. Here is the boundary of our conducting sphere. This is all full of copper everywhere. Okay. Now, Gauss's law says I'm going to integrate the electric field vector, taking its dot product, its component, with the surface vector. The surface vector, remember, is like this. It's always perpendicular to your surface, okay? And that is going to be equal to the charge inside. The charge inside depends on where you are, of course, what your surface is. Now, let's look at the left-hand side. We know that E is constant. Why? Well, because that's why I chose this sphere, this surface. So that E is constant everywhere. Take E outside. We also know that E is in the radius direction. So E dot ds is nothing but E times ds. Okay. Well, what is the surface area? It's 4 pi r squared. E times 4 pi r squared. Now comes the crucial point. This equals, I'm trying to find E. And I want to now relate it to what charge there is inside. How much charge there is inside this surface? Remember the beginning of the problem. It's a conducting sphere. Okay? How much charge there is inside? Q is the name of the charge. Do you have any idea what is the value of Q? At the beginning of the lecture, remember we said this is a conducting sphere. They all push each other apart and all the charges end up distributed equally on the surface. I am deep inside here. Within this radius R, inside of R is 0, right? That's what you can say because this is copper, this is conducting. All right? It is not always 0, but in this case, this is 0 because it's a conducting sphere. Okay? So I just found from Gauss's law that E times some number 4 pi r squared is 0. So E is 0. So at any radius less than the radius of the sphere, E equals 0. Now, remember, at the beginning, when we discussed what happens inside a conducting sphere, we already reasoned that electric field has to be 0. Because if electric field is not 0, the sphere is conducting, there is very little resistance or friction. So in a very short time, all these charges would move because there is a force on them. Electric field means force, okay? So therefore, electric field must be 0 inside the conductor, because if it's not 0, they will move out until it becomes 0. Clear? So I knew the answer already. The reason I made the example is to show you the simplest example of how Gauss's law, if you just apply it blindly, will give the right result. Okay? Because Gauss's law says at any closed surface, the integral of the electric field moving out, the E dot ds integral, must equal the charge inside. In the case of a conductor, the charge inside, any radius inside the conductor, is 0. So that mathematically gives you, from Gauss's law, the result that E is 0, which you could guess already, but in many problems you can't guess what the electric field is just like that. But if you use Gauss's law, you will get the result. Okay? So this was our first example. Now let me continue. I have done this when we were inside the sphere. Now B is when we consider points like this one. That are outside the sphere. Okay? Now what will happen? Well, the arguments are all the same. There is spherical symmetry. Gauss's law appears exactly the same way. So we have, once again, Gauss's law becomes E times just 4 pi r squared because E is constant over the surface. Right-hand side of Gauss's law says, write down here how much charge there is inside your closed surface. Let me point out the closed surface for you. Now my closed surface, my Gauss surface is this. Again, it's a sphere, but now it contains my charged copper conducting ball inside. Okay? So what is the charge inside now? Bir dakika yazmayı bırakın. Okay? So you think for yourself and answer this. When my sphere is outside the ball, what is inside? The ball. How much charge is there on the ball? Q. Okay? But that's an important point because the Q is on the surface. When I was inside the ball, I wasn't seeing Q further in from where I was. Now that I'm outside, all of the Q, as soon as I pass through the surface, and I'm interested in points that are outside the ball, I draw my Gauss sphere. What's inside? Now, instead of 0, it's the whole Q. Because it was right at the surface. If you are further in from the surface, charge inside with respect to your Gauss sphere is 0. When you move out, it's Q. In a step, it becomes Q. Okay? Notice I don't write Q of R because it's the whole Q now. Okay? So E equals Q over 4 pi R square epsilon 0. And in what direction? Let me now write it as a vector. In the radius direction, outward. Why? Because the charge is plus Q. So Gauss's law already gives me the plus sign. Okay? It's outward. So I found that in a conducting sphere, the electric field anywhere inside the ball is 0, anywhere outside the ball is this. And I noticed that this contains the total charge, which is concentrated on the surface, divided by the area of the surface. So this is just the charge per unit area. Remember, because it's conducting, the charge is distributed at equal density all over the surface. Okay? And Q divided by 4 pi r squared is just charge per unit surface area. We give this usually the symbol sigma, called the charge, surface charge density. What's this unit? Coulomb per meter squared, right? That's our area unit. So this finishes our first example. Let me do another example now. Okay, let me just give you the picture. So I have an insulating sphere. I have a total charge plus Q. And somehow it has distributed itself over a long time, all over the inside. Why all over the inside? Because they all repel each other. So it's best to be distributed evenly. But they will not all go to the surface, because this is insulating, yellow come. Okay? Clear? And I'm assuming that this insulating sphere has distributed the charges until they have stopped in equilibrium. And in this situation, from the center to the surface of the sphere, everywhere, the charge per centimeter cubed or meter cubed is the same. How much is it? It's just Q over the volume of the sphere, which is 4 pi over 3. R1 cubed. R1 is, of course, the radius of the sphere. So this is R1. Okay. And to make this a bit more interesting, this example, I'll add another sphere, a spherical shell here. And let's say this radius is R2. And total charge on this conducting spherical shell, okay, is minus Q, whatever it is. So it's, you have plus 3 coulombs on this ball and minus 3 coulombs on this enclosing shell. Use Gauss's law and calculate the electric field everywhere. Okay? So let's start from the outside. A, at a point R, at radius R from the center, which is greater than R2. What will happen? So here's my point. Outside the big spherical shell, I make up an imaginary Gauss surface. Of course, this is a problem with spherical symmetry, so my surface should be a sphere because all the points on that sphere will have the same electric field. Okay? So you always choose a surface that's going to be easy such that the electric field is constant on that surface. Okay? So let's complete the surface. Okay, here's my surface. Okay? So, again, E times ds is going to be Q total inside divided by epsilon 0. This is 4 pi r squared. What is the total charge inside this big sphere? What is it? What is the total charge inside that big sphere? 0. Thank you. Bravo. Okay. So the electric field is outside this sort of complicated configuration. Insulating sphere, conducting shell, plus Q, minus Q. If you are outside, doesn't make any difference. Total charge inside is 0. The details are not important. Okay? If I had put there 5 different shells with charges plus 3Q, minus Q, minus Q, minus Q, let's say. If you are outside, the net result is 0. Okay? Now let's move to the next part of the problem. Suppose R is between R2 and R1, then E times 4 pi R squared will be just Q inside over epsilon 0. Let me go back to the picture on the last page. So here's my surface now. How much charge is there inside? Plus Q. It doesn't matter how that charge is distributed. Inside is spherically symmetric plus Q. Okay? So, electric field strength is plus Q over 4 pi R squared epsilon 0. In what direction? In the radial direction. Okay? Does everybody understand this? Outside it was 0. In between the two shells, from R1 to R2, the electric field strength decreases as 1 over R squared times the plus Q inside. Okay? Any questions? Okay. Now everybody take out a piece of paper. Write down your name. Except the two gentlemen, you two, who came just now, of course. You can't ask what you don't understand because you are not here. So.